Hello dear student, the next topic of this lecture series based on the statistical physics is free energy. So what is free energy? This is also called Helmholtz free energy, which is represented by F, capital F. And it is defined as the difference of internal energy and product of temperature and entropy. Mathematically, it is written as F is equal to E, which is internal energy, minus T, which is temperature, and S is entropy. So this Helmholtz free energy is just the difference of internal energy and product of temperature and entropy. Now, since internal energy E, temperature T, and entropy S are all state functions, so F is also a state function. Now, what is state function? We know it that state functions are those functions which depend only on the initial and final positions irrespective of the path followed by those functions. They are independent of the path followed by the processes, only depend upon the initial and final positions. The physical significance of free energy, this is also important. By definition, we know that free energy is F is equal to E minus Ts. Now, change in F from position 1, let it be F1, to change to position 2, let it be F2 during any process can be written as small change is del F is equal to F2 minus F1. And this F2 we know that this is equal to E2 minus T2 S2 minus F1 again E1 minus T1 into S1. Now combining similar terms within the brackets, E2 minus E1 is equal to bracket T2 S2 minus T1 S1. Now this E2 minus E1 is equal to del E, and this is equal to del into product of temperature and entropy. For a isothermal process, T1 is equal to T2 is equal to T1, which is a constant. For a isothermal process, temperature remains constant. So this can be written as del F is equal to del E minus T. This T becomes constant, so it does not affected by any variation delta. So this becomes T delta S, because for isothermal process T is constant. Now in a reversible isolated process, the work done on the body, we know that, let it be represented as R maximum, work done. Del R maximum is equal to del E minus del Q. This is work done on the body. So on rearranging, del E is equal to del R max plus del Q. So putting equation number 2 into 1, so this del E can be replaced by this factor, these two terms. Del F is equal to del E, which is equal to del R max plus del Q, and this is minus T del S already in equation number 1. So del R max plus this del Q, according to second law of thermodynamics, this del Q is equal to T del S. Curly Q is equal to T curly S minus Ts. So these are similar but opposite terms and will cancel out. So we are left only with del R max. So this change in gives free energy. The change in this Helmholtz free energy is equal to del R max. The change in free energy equals the maximum work done, maximum work that a thermally isolated system can do. This is an important thing. So Helmholtz free energy, which is F, represents the useful work that a thermally closed system can produce. This is useful work. The Helmholtz free energy is determined for systems with constant temperature and volume, and this decrease in del F indicates the spontaneity of the chemical reaction. So what is its basic significance is that this free energy represents the useful work that a thermally isolated system can produce. So let's discuss about its differentials. Since the total differential of E, we know that d is equal to TdS minus PdV on combining first and second law of thermodynamics. We have discussed it many times. Now by definition, F is equal to E minus Ts. On differentiating it, dF is equal to dE, and we will differentiate this term by parts. So minus TdS minus SdT. Now putting equation number 2 in 1. So equation number 2 into 1. So dF becomes equal to dE. Putting equation number 1 into 2, basically, I have written it wrongly. Putting equation number 1 into 2. So dF is equal to dE, and dE from equation number 1 is equal to TdS minus PdV. So this is from equation number 1 minus TdS minus SdT. This is as it is from equation number 2. So on solving these four terms, this first term and this third term, they are equal and opposite. So they will cancel out. We are left with only minus PdV and minus SdT. This equation you can also remember. Now differentiating with respect to volume at constant temperature. At constant temperature, second term will become 0. So curly F upon curly V with respect to volume at constant temperature. So this term will become 0, and we are left only with minus P. Similarly, on differentiating with respect to T at constant V, at constant volume, in this case the first term will become 0. So we are left with curly F upon curly T at constant volume is equal to minus S, is equal to minus S. Thanks for listening and watching.